talk. We can hear you. You can hear us. It's very exciting. All right.
Okay, great. So hi, everyone. My name is Lennard, and today I'm going to talk about Simuliris, which is a framework for verifying concurrent program optimizations using separation logic. So this is joint work with Michael, Simon, Ralf, Hai, Robbert, Jeehoon, and Derek. So modern compilers are applying a lot of smart optimizations to make our programs run fast on modern hardware. And as an example, consider this C function here on the left. It operates on two integer pointers x and y. And while the details of it do not really matter, when the value at x is positive, it essentially multiplies the number stored in x and y by repeated addition in a while loop. Now, when we ask the Klang compiler to translate this function, it will do multiple optimizations. And one of them is to hoist the repeated loads from x and y out of the loop, replacing them by single loads into local variables n and m. And this optimization speeds up the program, as loads from memory are expensive and n and m can subsequently be placed in registers. But how can we prove the correctness of such optimizations? Well, in this case, you might think that it is obvious. As long as x and y do not change during the loop, the optimization can easily be seen to be correct. And that clearly holds true in a sequential setting. In a concurrent setting, however, the picture is less clear. You might imagine that some other concurrent thread also has access to x and y and is changing their value by writing to them, such as in the code on the right. Then, in fact, the optimized program can produce results that the unoptimized program could not. And as an example of this, assume that we execute the optimized program in a state where initially x is 1 and y is 99. First, the thread on the left loads from x and n gets the value 1. Then the scheduler switches over to the other thread and writes the new values of x and y. And after that, the left thread reads y into m, seeing the new value 42 written by the other thread, and the remaining code on the left is executed. Now, in this case, the optimized program produces the result 42 by using the old value 1 of x and the new value 42 of y written by the other thread. On the other hand, let's check if the unoptimized program can also produce that same result, 42. Well, we can see that the thread on the right will have to execute first, as otherwise the sum would contain 99, which would make it impossible to get to a result of 42. But now, since the unoptimized program will always read x after y, also the new value 2 will be read for x, so we will get the result 2 times 42. So there's no interleaving which can produce that same result 42 produced by the optimized program. So the optimized program can produce results that the unoptimized program could not, and the compiler should not be allowed to do such transformations. There must be something more going on here. And actually, the reason why the optimization is still correct is that there is a data race between the two threads in this example, since one thread is reading while the other is writing, without any synchronization. And in C and C++, programs with data races have undefined behavior, or short to UB. This means that the programmer has to guarantee the absence of data races, and so the compiler can assume that no concurrent thread is writing to x or y. So the optimization is correct, but proving so requires reasoning about concurrent program optimizations relying on UB of data races and involving loops. So while there's a lot of interest in verifying compilers, there's only little work involving data races. So let me focus on the works dealing with data races in this overview. Works by Sevcik, Morissette, and Vafayades have investigated eliminations and reorderings based on data races in different memory models, but only on finite traces. Thus, the approach cannot handle potentially unbounded loops akin to our motivating example. Another line of work on CAS ComCert and concurrent ComCert is in principle able to perform optimizations exploiting data races, although they don't do them in practice. But these approaches cannot justify some known optimizations around synchronizing operations like atomic reads, due to the way synchronization is modeled. Now, as part of our work, we developed an approach that does not have these limitations. And our key idea for verifying data race optimizations is to employ the concept of ownership from separation logic. Let's consider the example code again. With our approach, we prove a simulation. And our simulation relation features a pre and post condition starting from a trivial precondition. Now, since an unsynchronized read from y is reachable in the unoptimized program, our proof rules then allow us to obtain partial ownership of y, since we know that no concurrent thread can be writing to it. And we express this through the points to connective of separation logic, and we add it to the precondition. Similarly, since read from X is reachable, we also obtain ownership of X. And we can then retain this ownership throughout the whole loop, which allows us to justify that the two code segments indeed compute the same result. Now, to implement this formally, we have developed Simuliris. Simuliris cannot just be used to verify data race-based optimizations, but rather is a language-generic simulation framework. And our simulation relation satisfies a strong soundness result, namely fair termination preserving contextual refinement. Simuliris provides many common proof principles, such as coinduction, and allows the derivation of domain-specific logics on top. And we have used it to develop two such logics. First, a logic for data race-based optimizations. And secondly, we have re-implemented and extended the simulation logic from the Stack Borrows paper by Jung et al., and it now has support for concurrency and other new reasoning principles. Finally, all of this has been fully mechanized in the Coq proof assistant using the Iris framework, and our Coq artifact is freely available and has been deemed reusable. Now, for the rest of this talk, I'd like to tell you more about Simuliris as a framework and the principles underlying it, and then focus on our logic for data race-based optimizations. First, let's take a look at our simulation. Our powerful simulation relation is essentially the key ingredient of Simuliris. It basically combines the typical shape of a coinductive simulation with features known from modern separation logics. Formally, our simulation relation relates a source expression for the unoptimized program and a target expression for the optimized program, ensuring that every behavior of the optimized program can also be exhibited by the unoptimized program. What behavior here precisely means, that I will get to later. Now, as techniques commonly used in verifying compiler optimizations, our simulation inherits the ability to coinductively reason about loops and recursion, as well as the ability to exploit UB in the source program. And our simulation also features a very flexible stuttering mechanism. On the other hand, to easily compose simulations for different program parts, our simulation has pre- and post conditions, P and Q, that need to hold before and after simulating the source and target expressions. That is known from relational separation logics, and it allows us to give modular proof rules. And since P and Q are separation logic assertions, we can use elegant ownership reasoning with the ability to use custom resources known from Iris to encode new reasoning principles. And finally, in Coq, we can also reuse the Iris proof mode. So let me show you some of these features. And first of all, let's take a look at how flexible stuttering helps to get compositional proof rules. In particular, in addition to a powerful simulation relation, our framework also features source and target triples to temporarily focus reasoning on one side of the simulation. You can essentially imagine these as the triples from a total correctness separation logic. And we can flexibly switch between simulation, source, and target reasoning at any time. In the background, this is enabled by a very flexible stuttering mechanism. Our simulation allows us to do unbounded but finite stuttering of source and target without explicitly counting steps anywhere. But to the user of our logic, this is exposed abstractly through these source and target triples. Next, let me demonstrate with a very simple example what separation logic reasoning brings to the table in terms of justifying optimizations. And for the rest of this talk, we are going to consider programs in our functional example language Simulang. So the simple unoptimized program on the left here allocates a new reference x with value 42, then calls some unknown function f, and afterwards reads from x again. Intuitively, we'd like to optimize that last read away, directly using the value 42, because f should not have changed the value we've just written to x. Now, formally, we do this by proving a simulation starting from a trivial precondition. And first, we execute the allocation on both sides, and to obtain ownership of x expressed through the points to connective. Since we are working in a relational separation logic, we have 2 points to connectives for source and target. Next, we reach the call to f, and we use the frame rule of separation logic to retain the ownership of x over the call. And finally, we can perform the load in the source using the ownership of x to justify that both sides return 42. Now, looking at this, the crucial step is that we could retain ownership of x while calling f. And opposed to traditional separation logic reasoning, we do not require any knowledge about f in the precondition. F can essentially be completely unknown to us. But since the call happens on both sides of the simulation, we can still skip over the call. For this, unknown code needs to respect our ownership, and that is part of the soundness result of our logic. Now, let's look at how this integrates with co-inductive reasoning for reasoning about loops. And this is a slight modification of the previous example. Instead of just calling f once, we loop until f returns false, and we pass it the value read from x in each iteration. You might imagine that f does some computation on a global variable. And again, we'd like to eliminate the redundant loads from x in each iteration of the loop. Now, we once again start by allocating ownership, but now we need to reason about the loop. And for that, Simuliris provides a generic co-induction principle from which we can derive one for reasoning about loops. Let's assume that we currently have a while loop on both sides of the simulation with potentially different conditions and bodies. Then we can pick a loop invariant I and instead have to prove a simulation after unfolding the loop for one step. When the loop has terminated in result values vs and vt, we can prove the old post condition q. Now, in addition, we need some way to encode our co-induction hypothesis. After simulating the loop for one iteration, we should be done with the proof by co-induction. And this we encode as part of our post condition. The rule adds a disjunct, which, as an alternative to proving the old post condition q when we bottom out of the loop, also allows us to just establish the invariant I again and take another iteration. And in the case of the small example here, we'd pick the ownership of x for I, and then the rest of the proof is straightforward. Now, even though the previous two examples here were really simple, they show the benefits of ownership reasoning for verifying optimizations. But verifying them was actually quite easy because it's unsurprising that we can obtain ownership of local variables. But what about optimizations on function arguments, such as in the motivating example I showed in the beginning, where the ownership argument is much less clear and actually relies on undefined behavior? Well, for that, let's next turn to our logic for data race-based optimizations. And first, let's focus on a very simple example. In contrast to allocating a memory cell x as in the previous examples, the function on the left here takes a pointer x as argument, first writes 41, then 42 to it, and then reads from it again. And intuitively, we'd like to eliminate the first store to x, since it is directly overwritten, and replace the load from x with the value 42 that was just written before. And this is what the simulation here says. Now, in ordinary separation logic verification, we would assume ownership for the function argument x in the precondition. Then the caller would have to provide us with that ownership when calling the function. But for compiler optimizations, we cannot just assume that the environment, in particular the caller, is cooperative. The caller might also have passed the pointer x to other threads, but the caller should still be able to call the function with argument x as long as that is a valid program. So we cannot just assume full ownership. Instead, we require a public value relation. For the variable x, we get two concrete values, xs and xt in source and target, and they should be in some sense similar. For integers, this just means that the two integers should actually be equal. But for pointers, we require the contract that the stored values at these locations are in turn related by the value relation, and thus behave similarly when reading and writing. And as long as this contract is upheld, anyone is allowed to access these locations. But now, how can we use this to perform optimizations? In the previous examples, we crucially relied on having ownership to perform the optimization. Well, despite this contract, we should be able to temporarily break the contract and obtain ownership as long as we can ensure that no other thread will notice us doing so. And the idea for that, as I already mentioned, is that we can justify that this is the case whenever conflicting accesses would be data races. So we can obtain ownership on unsynchronized accesses since no other thread is allowed to observe this. And what kind of ownership can we obtain in this way? Well, when an unsynchronized write is reachable in our thread, we know that all concurrent accesses would be data races, so we can obtain exclusive ownership. Let us try to formulate this formally. Assume that we currently need to prove a simulation, written in the conclusion of the inference rule here, where the source expression contains an unsynchronized write to a public location ls that will be executed next. Then we can transform the goal to a simulation where we additionally can assume ownership of ls and lt, denoted by the points to connectives, and those point to related values vs and vt. So that isn't too complicated, so let us actually try to apply this to our example. We start out assuming that xs and xt are the value relation. And we know that the next instruction in the source is an unsynchronized write, so we can apply the rule to obtain ownership. Then we can use this ownership to do the first write in the source. At this point, note that the two locations xs and xt point to different values, so we've temporarily broken the contract. Next, we do the writes in source and target, bringing xs and xt in sync again. And finally, we can justify that the load in the source will also produce the value 42, since we still have ownership of x. So this all looks well and allows us to prove our simulation. But there is something odd here. What prevents us from just applying the rule a second time to gain ownership again? Clearly, that would be unsound, as the points to connective is supposed to be exclusive. And the rule I just showed to you does not suffice yet to rule this out. Well, to fix this problem, we should somehow track the locations for which the current thread has already obtained ownership. And concretely, we do this by extending our simulation relation with the current thread ID pi, and then add an exploit assertion that does this tracking in a set of locations C. For the rule to be applicable, we should be sure that we have not obtained ownership for the source location ls yet, denoted in an additional premise. And in the new goal, we remember in the set of exploited locations that ls was exploited through an unsynchronized write, denoted by w. And with that, we can actually validate this rule. And I should note that we use Simuliris' flexible ghost state mechanism inherited from Iris to define this exploit assertion. Now, we can actually generalize this rule a bit more to also be applicable if the unsynchronized write is just reachable, but not necessarily the next instruction. And a similar rule also holds for unsynchronized reads, with the difference being that we only obtain fractional read-only ownership instead of full ownership. Now, there's one question that remains. Do we ever have to give up that ownership again? And the answer should be yes. Other threads should not be prohibited forever from using these memory locations for which we have obtained ownership. Effectively, we can maintain ownership until our thread does an action that is observable by other threads. This includes forking, calling unknown code, or doing a synchronizing write. For instance, the rule for sequentially consistent writes requires that the exploit set is empty in its precondition. So we need another rule for giving up ownership and removing the location from the exploit set again. And this you can find in our paper. And with that, we actually have all the ingredients in hand to verify a translation of the motivating example into our language. We first obtain ownership of x and y, partial ownership, since unsynchronized reads from them are reachable. And then we initiate coinduction for the loops using the ownership we just obtained for the coinduction hypothesis. And with that, the rest of the verification is essentially straightforward, using the ownership we have just obtained. And finally, we return the ownership after the loop. So I hope I've convinced you of the usefulness of Simuliris by now. But what are we even proving when showing a simulation in Simuliris? Well, our soundness result establishes a so-called fair termination preserving contextual refinement. And let me briefly explain what this means. First of all, if the optimized program can terminate with a result, then also the unoptimized program should be able to produce a similar result. That is a simple result refinement. Secondly, optimizations should preserve termination, so the optimized program should only be able to diverge if also the unoptimized program can diverge. And importantly, we have verified this under the assumption of fair scheduling. We do not use this to gain new proof rules, but rather because we think that it gives a more realistic soundness result. And while fair termination preservation has incomparable strengths to plain termination preservation, realistic schedulers are fair and don't just starve some threads. So an unfair diverging schedule in the unoptimized program should not just allow the compiler to introduce non-termination even under a fair scheduler. And finally, all of this should hold for any surrounding program under the assumption that the source program has no undefined behavior. Now, let me note that the soundness proof was actually quite challenging, in particular due to the fairness requirement we impose and due to the flexible stuttering allowed by our simulation. But luckily, we have proved this once and for all, so that all domain-specific logics we define using Simuliris can just reuse the hardcore of our soundness theorem. And to close this talk, let me now mention some of the other things you can find in our paper. First, you can find more details about our underlying logic and an overview of the challenging soundness proof. As for our data race logic, we present more examples of what our ownership approach can handle, and we explain how we've verified its soundness. And for our stacked borrows logic, you can find an overview over how we have extended the optimization proofs from the original paper to concurrency and added additional reasoning principles. And with that, I'd like to finish this talk, and I'm happy to take any questions. Thank you.
So let's start with a question from the room. I see there's at least one typed in. Who would like to, does anybody here have a question? Yeah.
Oh, yeah. Nice talk. Yeah, okay, can you hear me? ABC, testing,
Yes, I can hear
testing,
you.
mic test. Yeah, right, good. Okay, nice talk. Unsurprisingly, I'm going to ask a weak memory model question, which is that, so your proof rule, it looks like it gives up all ownership at the point that it hits a synchronization barrier.
Yes.
And I was wondering, are there interesting optimizations, especially in languages like Rust, that this doesn't allow you to verify? So I'm thinking of something like doing constant folding across the use of an arc. So where the effect of the arc is just the cells it owns. And so your rule, because when you touch the arc, you've done a synchronization, you won't be able to do any optimization across that. So I was wondering if there are interesting optimizations that are used in practice that you've seen problems with.
So first of all, let me note that I'm not a weak memory expert, and actually the memory model that we use does not model weak memory. So yeah, it's basically a sequentially consistent model that we use. Yes. So I'm not sure about your example. Maybe if we can take this offline and you can like send me the example code for that. We could look at it. I do not have it currently in my head.
Okay, great. So I have a question for you. It's just about the notion of UB that you have. This is a UB as in C, right? So reading a uninitialized value is undefined behavior. Is that right?
Well, we do not have uninitialized memory per se. Well, if you just come up with some location that you have not allocated, then you cannot read it. Yes, but
yeah, I guess that's my question. So is read introduction a valid transformation in this world? Sounds like the answer is no.
Well, if you have ownership of that logically, then you can do it. If you have ownership of that location in the separation logic sense.
Right. Okay. Okay.
So you might have some location, and well, especially if you've locally allocated the location, then you of course have ownership, and you can introduce more reads if you want to. If you are talking about things like you've got a location from a function argument, for instance, and you can somehow justify that you've got ownership of it, for instance, through unsynchronized accesses in your function, then you could also introduce additional reads, if that answers your question.
Yeah, it does. Thank you. Okay. Well, then let's thank the speaker. Thank you so much.
Thanks.